Hello dear viewers, welcome to TV Math Hub. This is your home for clear and practical mathematics. In our today's session, we shall be looking at more revision questions for linear algebra. And here we begin with this question. It says, define a vector space and give 3 examples. So we shall look at the definition of a vector space. So we shall be defining a vector space. So we shall be saying a vector space over a field F, a vector space. You define a vector space over a given field. So a vector space over a field F is a set V equipped. This is a set V which is equipped with two operations, equipped with two operations, that is vector addition, and scalar multiplication, satisfying the following axioms for all u, v, w that are picked from the vector space V, and the scalars A and B, picked from the scalar field F, and the scalars A and B picked from the scalar field F. So to define a vector space, you have to define it over a given field, and it should be equipped with the two operations, that is vector addition and scalar multiplication, for which the following axioms should be satisfied. So let us look at the axioms. The first one is what we call associativity of addition. Associativity of addition. For this case, we shall have that if you are having u plus v, if you are having vector u plus vector v, then you add their vector w. This should be true or should be same as having u plus v plus w. So adding this to this should be same as having u plus this one. This is what we call the associativity of addition. Then two, we have what we call commutativity. We have what we call commutativity of addition. So for commutativity of addition, here we say that if you are having vector u plus vector v, this should be same as having vector v plus vector u. That is what we call commutativity of addition. Then three is what we call identity. Identity element for addition. So what this one means is that there should exist. This means that there exists a zero which is picked from the vector space V, such that when you get u plus a zero vector, you get u. So this is what we call the identity element or for addition. So identity element, there exists a zero element such that when you get a vector plus that zero element, you remain with the same vector. So axiom number 4 is what we call the inverse element for addition. Inverse element for addition. So the inverse element for addition means that this means that for each vector, u that you pick from V, for each vector u that you pick from V, there exists negative u, which is also picked from the same vector space V, such that when you get u plus negative u, you will get what we call an identity element, which is a 0. You get what we call an identity element, which is 0. Then the fifth one, so these are dealing with what we call the vector addition. So the vector addition implies that when you have u plus v, then when you get u plus v, this result should be still in the vector space. Then for the scalar multiplication, it means if you have a scalar a, you multiply it with a vector u, then this should also be in what we call the vector space V. So these are some of the axioms that are related with vector addition. And now we want to look at some of the other axioms that are related with what we call the scalar multiplication. So number 5, we shall begin with what we call the distributivity of scalar over vector addition. This one implies that when you pick a scalar a from the field, if you pick a scalar a from the field, then you pick u and v from the vector space, then when you have a into u plus v, this should be same as a times u plus a times v. That is what it means, meaning that you are distributing the scalar over the vector u and v. This is the vector addition u plus v. So when you have a into u plus v, it should be same as having a times u plus a times v. So that is what we call the distributive property for scalar multiplication over vector addition. Then the next one, that is the 6th, we shall have what we call a distributivity, or that is the distributive property still. So that is distributivity of scalar addition over multiplication, over field multiplication. So this means that when you have two scalars, for example a and b, which are picked from the scalar field F, and you have vector u, which is picked from the vector space V, then if you have a plus b into u, this should be same as a times u plus b times u. This should be the same for vector u. So this is the distributive property for scalar addition over multiplication. So we have a plus b into u, it should be same as a times u plus b times v. So then the next one is what we call compatibility of scalar multiplication. So let us look at the next one, compatibility of scalar multiplication. So what does this one imply? This implies that if you have two scalars, a and b, which are picked from the scalar field, scalars are picked from the scalar field, then the vector is picked from the vector space. So u is picked from v. Then if you have a into b times u, this should be also same as having ab into u. So when you have two scalars a and b picked from the scalar field F and u is picked from v, when I have a scalar outside, this is like when you have 2 into 3 times u. This should be same as having 2 times 3 multiplied by u. So that is what it means. The two must be the same. Then the last one, that is number 8, axiom 8, is what we call identity element. Identity element for scalar multiplication. Identity element for scalar multiplication. This one says that if you get 1 is a scalar, that is 1 is picked from the scalar field, and u is picked from the vector space. So 1 times u should be same as u. 1 times u should be same as u, where we call this one, where 1 is the multiplicative identity. Where 1 is the multiplicative identity. Where 1 is the multiplicative identity in the scalar field F. So additionally, it is important to note the operations. It is important to note that the operations must satisfy one, the closure property, that is u plus v should be picked. U plus v, if you have u picked from v and v picked from the vector space v, then u plus v must also be in the vector space. And likewise, when you get a scalar a, you multiply it with u, this should also be in the vector space. So all these 10 axioms here must be satisfied for a given non-empty set to qualify to be called a vector space. So these must be satisfied first. So that's why we said here when we are starting that these two operations must be satisfied. That is vector addition. In other words, u plus v should be picked from v, and the scalar multiplication, that is a times u, should be in v. So those are the 10 axioms that must be satisfied for a given non-empty set v to qualify to be called a vector space. So that is all about the definition for a vector space. So when they ask for the definition of vector space, you should be able to give these axioms. You should be able to state these axioms. So next we look at the examples. Next we want to talk about 3 examples of vector spaces. According to the question, we need to define a vector space and give 3 examples of vector. So now looking at examples of vector spaces, so we have got different examples, but we shall give some few. So we have what we call Rn space. So the Rn space, this is what we call the n-dimensional Euclidean space. N-dimensional Euclidean space. That is R to power n space. So here, these are vectors. These are vectors of any tuples of real numbers with component-wise addition and scalar multiplication. For example, when you are talking about R2, so R2 you have what we call component-wise addition and scalar multiplication. If you are dealing with xy, so that is the R2. So R3 we have R4 up to Rn. So Rn, it has got, this is what we shall be calling any dimensional Euclidean space. So that is one of the examples. Then 2, another example is what we call the set of all polynomials. So when we talk about the set of all polynomials, the set of all polynomials, with real coefficients, real coefficients of degree at most n, and this is in most cases denoted by p. This is denoted by p of n having r implying they are real coefficients. So when you have the set of all polynomials of real coefficients of degree at most n, denoted by this, it also qualifies to be called a vector space, for which the addition is polynomial addition and scalar multiplication distributes over the coefficients. Then the third one we can talk about the set of all continuous, the set of all continuous functions, the set of all continuous functions, for example C of 0, 1. So we have got functions on this interval. This is the interval on the interval 0, 1, on the interval 0, 1. So the set of all continuous functions, this one here on the interval 0, 1, also qualifies to be called a vector space, because here addition is pointwise. For example, the addition, if you are having a function f plus g of x, this is same as having f of x plus g of x. So the addition is possible. Then the scalar multiplication, if you have alpha of f into x, this is same as alpha f of x. So the addition and scalar multiplication are defined as that. So that one also qualifies. And we have also got the matrix space. The matrix space, that is the set of all matrices, the set of all m by n. You can also talk about that, the set of all m by n matrices, where the coefficients, or what we call the entries, are real numbers. So that one is also what we call a vector space. So these are some of the different examples of vector spaces that you can easily mention. So there are also others. You can add on some more examples. And that's all about our part A, which was about to define a vector space and give 3 examples. So basically we can come to part B. Part B says when a vector is said to be linearly dependent. When a vector is said to be linearly dependent. So to look at this, we shall give the definition for linear independence of vectors. So let us talk about linear dependence of vectors. So we need, when are these ones, when a vector is said to be linearly dependent. So we shall be saying that a finite set, or if you have a set of vectors, a finite set of vectors, for example, let's have v1, v2, and up to vn. If we have this set here, a finite set of vectors consisting of v1, v2 up to vn in a vector space, is linearly dependent if there exists scalars, for example, alpha 1, alpha 2, up to alpha n. Very important that not all 0, these scalars here must not all be 0, such that when you get alpha 1 v1 plus alpha 2 v2 plus up to alpha n vn, this should be equal to 0. Where this 0 here, where this 0 is what we call the 0 vector, is the 0 vector. So we shall be saying that if you have a finite set of vectors v1 up to vn in a vector space, then it will be linearly dependent if you get scalars alpha 1, alpha 2 up to alpha n. And the most important thing is not all these scalars should be equal to 0. Otherwise, if they are all equal to 0, then we shall say that this given set of vectors is linearly independent. So for this case, if not all of these are 0, then, and this one also is true that alpha 1 v1 plus this gives you a 0 vector, then we shall say that this set is linearly dependent. Equivalently, you can also say that at least one vector in the set can be expressed as a linear combination of others. So if no such non-trivial combination exists, that is, if the only solution to the scalars, if the only solution is all alpha I equal to 0, then this set will be said to be linearly independent. That is for I equaling to 1, 2, up to n. In other words, if you have a finite set of vectors this in a vector space, and you find that there exists when alpha 1 is equal to alpha 2, when all the alpha are equal to 0, then alpha 1 v1 plus alpha 2 v2 up to alpha n vn is equal to 0, then we shall say it is linearly independent. But if you are able to get some of the scalars not equal to 0, then we say such a set is linearly dependent. So you should be able to distinguish between linearly independent and linearly dependent vectors. Okay, so that is about the definition for linearly dependent vectors. So we shall look at the next question. Determine whether the following sets of vectors are linearly dependent or not. We need to determine whether this set of vectors is linearly dependent or not. Okay, so let us look at this. Basically, we have got two ways of how we can do this. One, as we have seen by definition, you can seek for the scalars. That is the first method. You can seek for the scalars alpha 1, alpha 2, and alpha n. So if this is, for example, v1, our v2, and v3. So if you are able to get the scalars alpha 1, alpha 2, and alpha 3, such that you have alpha 1 v1, that is the linear combination. When you get the linear combination of these vectors with the scalars alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, and you equate this to a 0 vector. If you equate this to the 0 vector, then you go on and obtain the values of alpha 1, alpha 2, and alpha 3. If alpha 1 is equal to alpha 2, which is equal to alpha 3, which is equal to 0, then these vectors will be said to be linearly independent. But if one of them is not equal to 0, if one of these ones here is not equal to 0, maybe alpha 1 or alpha 2, or all of them are not equal to 0, then we shall say that the set is linearly dependent. So this is one method. So you seek for the scalars alpha 1, alpha 2, and alpha 3, such that you equate this linear combination to 0. And when you equate this linear combination to 0, it means you are having something like this. Alpha 1, v1. v1 is this. That is 1, negative 2, and 1, plus alpha 2 into 2, 1, negative 1, then plus alpha 3 into 7, negative 4, and 1, which is equal to 0. This is a 0 vector in a 3, that is in R3, so that is 0, 0, 0. So in other words, you can easily form one equation here. This is alpha 1 plus 2 alpha 2 plus 7 alpha 3. So multiply this one with this, then add the corresponding components. Then this is negative 2 alpha 1 plus alpha 2, then minus 4 alpha 3. Then the last one is alpha 1 minus alpha 2, then plus alpha 3. So all these should be equated to 0, 0, 0. So you will obtain the three equations. That is alpha 1 plus 2 alpha 2 plus 7 alpha 3, which is equal to 0. Then minus 2 alpha 1 plus alpha 2 minus 4 alpha 3, which is equal to 0. Then alpha 1 minus alpha 2 plus alpha 3, which is equal to 0. So solve these equations, get the values of alpha 1, alpha 2, and alpha 3. Then if all of these scalars are equal to 0, then it means the set here is linearly independent. But if one of them or all of them are not equal to 0, then you say it is linearly dependent. So that is how we get that one. But there is one other method you can also use, which I think will be a bit easier. That is by getting what we call the determinant. So you can easily get the determinant of a 3 by 3, and from there, then you give the conclusion depending whether the determinant is equal to 0 or not. So I think that one would be the easier method. Though you can also use this same method, you also get the answer. But this one is a bit wrong compared to when you can use what we call the determinant. So let us look at the one which is a bit shorter. So the one that is a bit shorter is the one where we get the determinant. So we have this set here. We have our set S. So we have our set S, which is consisting of 1, -2, and 1. We have 2, 1, -1, and we have 7, -4, and 1. So that is what we are having. I want us to use the method of determinant. So here, to determine linear dependence for a set in Rn, so you can form the matrix with the vectors as columns or rows and check if its rank is less than the number of vectors, or if the determinant is 0 for a square matrix. So if the determinant is 0, then you can give the conclusion that this given set is linearly dependent. Okay, so let us look at that. That one is a bit shorter compared to the previous one. So let us look at that. So I will form the matrix. Let me call it A, consisting of, I will write this in column form: 1, -1, 1, -2, 1, then 2, 1, -1, then 7, -4, and 1. So this is my matrix. So I will get the determinant. I will compute the determinant of A. So compute a determinant of A. So the determinant will be, a determinant of A will be same as, so get the determinant of this. Determinant of 1, 2, 7, -2, 1, -4, 1, -1, 1. So the determinant will be same as, so as usual, how we get the determinant, you eliminate this one and this one first. So you have 1 into 1 into, so remove this and this. That is the first row, first column. So you get 1, -4, -1, and 1. Then -2, minus this value, into the determinant of when you eliminate the first row, second column. We get -2, -4, 1, and 1. So plus then 7 into the determinant, remove this one and this. Get -2, get 1, 1, -1. So from here, compute the determinant. So this will be same as having 1 into 1 times 1 is 1, minus -1 times -4 is +4. Then minus 2 into -2 times 1 is -2. Then we are subtracting 1 times -4, which is -4. Then again we add there 7 into, multiply this and this to give you 2, subtract 1. So that is what we shall get. So this will be same as, this is 1 times -3. 1 times -3 is -3. Then minus this and this will give us, -2. -2 times -2, it will be plus. So this will be plus 4. Then this is 7. 7 into 1, that is 7. That will be equal to, so this will be 7. Okay, so -2 plus 4 is +2, not -2. So this should give us a minus here. This should give us a minus here. So this is minus. So this will be equal to 0. So the determinant of A is equal to 0. So we shall give the conclusion that, since determinant of A is equal to 0, then the matrix, then it means the matrix is singular. That is, the rank is less than 3. So the vectors are linearly dependent. Since determinant of A is equal to 0, the matrix is singular. The matrix is singular. The matrix is singular. In other words, the rank is less than 3. And so the vectors are linearly dependent. The vectors are linearly dependent. So if you compute the determinant, and the determinant is 0, then you conclude that this set here, or these vectors here, are linearly dependent. But if the determinant is not equal to 0, if you get the determinant not equal to 0, then it means your vectors are linearly independent. So that is how we distinguish between dependent and independent vectors. So this one is a bit shorter compared to when you first equate the linear combination to 0. So that is our part 1, determine whether the following sets of vectors are linearly independent or not. So we have computed, place this one here in what we call the matrix form. Then from there, compute the determinant. If the determinant is 0, they are linearly dependent. If the determinant is not equal to 0, if the determinant is equal to 0, they are linearly dependent. Then if the determinant is not equal to 0, they are linearly independent. What I mean is, if the determinant of your vectors here, so you have formed your matrix A and you are getting the determinant 0, this means the vectors are dependent. That is linear dependence. Then if the determinant is not equal to 0, then this shows that the vectors are independent. So that is what it means. So place this in matrix form, compute the determinant. If the determinant is 0, you know what to conclude with. If the determinant is not 0, you know what to conclude with. So that is how we get to know whether the vectors are dependent or not. So the last one is this. We can try that one as well. So we are having this. So we can let our A to be our matrix, which is consisting 3, 4, then 1, negative 3. Okay, so from there, we obtain, let us compute the determinant of A. Compute determinant of A. So compute the determinant of A. So the determinant of A will be same as taking the determinant of 3, 4, 1, negative 3. So this one here, we multiply this with this to give us negative 9 minus 4 times 1 is 4. This is negative 13. This is negative 13. So negative 13 is actually not equal to 0. So we can see that the determinant of A is not equal to 0. So it means the vectors are linearly dependent. So if that is true, so we can now say, since the determinant of A, is not equal to 0, the matrix, it means the matrix has full rank. In other words, the rank is 2, has full rank of 2. So this means the vectors are linearly independent. So for linearly independent vectors, the determinant is not equal to 0. If the determinant is 0, then they are linearly dependent. So that will be answered. So lastly, we need to look at this question. Write the vector u, which is given as this, as a linear combination of u1, u2, and u3. Then show that this is a linear combination of the vectors. Okay, so we shall follow the same method. We'll do part 1, then you should be able to show for part 2. So write the vector u as a linear combination of u1, u2, and u3. So this is how we do that. So basically we are given u1, u1, which is 1, 1, 1. We are given u2, which is 1, 2, and 3. We are given u3, which is 2, negative 1, and 1. So we need to express u, which is given as 1, negative 2, and 5, as a linear combination of u1, u2, and u3. So that is basically what we are interested in. We need to express this as a combination of these ones here. So how do we do that? So what we need here is, we shall seek for the scalars here. We seek the solution. We seek for the scalars. Alpha 1, alpha 2, and alpha 3. We seek for the scalars alpha 1, alpha 2, and alpha 3, such that when you get alpha 1, you multiply it with u1. You add there alpha 2, you multiply it with u2. You add there alpha 3, you multiply it with u3. You get u. You want to express this as a combination of the scalars and the vectors u1, u2, u3 with the scalars alpha 1, alpha 2, and alpha 3. So this is writing u as a combination of the scalars and the vectors. So we need this. We need to simplify this, get alpha 1, alpha 2, and alpha 3. Then from there, we shall be able to show whether U can be written as a linear combination of U1, U2, and U3. So let us continue and solve for alpha 1, alpha 2, and alpha 3. Okay, so looking at that, let us have alpha 1 into U1. U1 is 1, 1, 1, plus alpha 2 into U2. U2 is 1, 2, and 3. Then plus alpha 3 into U3, 1, negative 2, and 5. This should be equal to U. Okay, this is not U3. This is U2. U3 is here. So U3 is 2, negative 1, and 1. Then we need to equate this to 1, negative 2, and 5. So that is basically what we shall do. So here, multiply this one with this. I want to multiply this one here to give us alpha 1. Multiply it with this, alpha 1, alpha 1. Add it with this is alpha 2. This is 2 alpha 2. This is 3 alpha 2. Add it with, multiply alpha 3 inside here, 2 alpha 3, negative alpha 3, then alpha 3. Equate this to 1, negative 2, and 5. Okay, so equate and add and equate the corresponding components. So alpha 1 will be added with alpha 2 will be added with this, which will be equal to this. So I will get the equations out. Alpha 1 will be added with alpha 2. We shall add it with 2 alpha 3 to get 1. Then also alpha 1 will be added with 2 alpha 2 minus alpha 3 to get negative 2. Next, alpha 1 will be added with 3 alpha 2 will be added with alpha 3 to get 5. So these are the equations that we shall be having. So from these equations, this is equation 1, equation 2, this is equation number 3. So I will solve these equations to obtain the values of alpha 1, alpha 2, and alpha 3. So let us do that. So let us consider equation 1 and 2. When I consider equation 1 and 2, I have alpha 1 plus alpha 2 plus 2 alpha 3, which is equal to 1. I have alpha 1, 2 alpha 2 minus alpha 3 equaling to negative 2. So I will eliminate alpha 1 by subtracting. So when I do that, this will go alpha 2 minus 2 alpha 2, that is negative alpha 2. 2 alpha 3 minus alpha 3, that is 3 alpha 3, which is equal to 1 minus 2, that is plus, that will be 3. So this will be equation number 4. Okay, so having that, I will go on now. I also eliminate alpha 1 using equation 1 and equation 3. So again, I will consider equation 1 and 3. When I consider equation 1 and 3, I have alpha 1 plus alpha 2 plus 2 alpha 3, which is equal to 1. I also have alpha 1 plus 3 alpha 2 plus alpha 3, which is equal to 5. So I can easily eliminate alpha 1 also by subtracting. So when I do that, I will be able to remain with, okay, so I will be able to remain with alpha 2 minus 3 alpha 2, this is minus 2 alpha 2. 2 alpha 3 minus alpha 3, that is plus alpha 3. This is equal to 1 minus 5, that is negative 4. So that is equation number 5. This is equation 5. So we have equation 4 and 5 consisting of alpha 2 and alpha 3. So we shall go on now and consider, let us consider equation 4 and 5. So we shall have, for that case, so we need to again eliminate one of these two unknowns. So first of all, we make sure the coefficients are the same. Let us put 2 there, we put 1 there. So we have negative 2 alpha 2 plus 6 alpha 3 is equal to 6 minus 2 alpha 2 plus alpha 3 is equal to negative 4. And this we shall again subtract. So when we do that, this minus that, this will be 0. So 6 minus alpha 1, this is a 1. So that is 6 alpha 3 minus alpha 3, that is plus 5 alpha 3. This is 6 minus 4, that will be 10. So we have 5 alpha 3, which is equal to 10, which gives us alpha 3 as a 2. So we have alpha 3 as 2. So after getting that, we can go on and get the values. We can go on and get the values of alpha 1 and alpha 2. So let us consider from 4. From 4 we have negative alpha 2 plus 3 into alpha 3, which is 2, which is equal to 3. So minus alpha 2 will be equal to 3 minus 6, which is minus 3, and alpha 2 will be equal to 3. So we have got alpha 2, we have got alpha 1, alpha 2 and alpha 3. So we need alpha 1 now. So let us look at alpha 1. So we can use one of the equations. We can use equation number 1, alpha 1, alpha 2 to alpha 3. So from 1, which says alpha 1 plus alpha 2 plus 2 alpha 3, which is equal to 1. So that is by using equation 1. Yes, that one. So this will be same as alpha 1 plus 3, 2 times 2, 2 times 2, which will be equal to 1. So alpha 1 plus this is 7 is equal to 1. So alpha 1 will be equal to negative 6. Okay, so we have got alpha 1, alpha 2, and alpha 3. So our main question was to express this in terms of U1, U2, and U3. And we have seen that is possible by seeking the scalars alpha 1, alpha 2, and alpha 3, such that we write this equal to that. So therefore, U can be expressed as a linear combination of U1, U2, and U3 by saying that U is same as alpha 1, U1 plus alpha 2, U2 plus alpha 3, U3. So in other words, U is same as alpha 1 negative 6, U1 plus alpha 2, which is 3, U2 plus alpha 3, which is 2, U3. So if this is possible, then it means you can easily express U as a linear combination of U1, U2, and U3. So that is how best we do this question. So write U as a linear combination of U1, U2, and U3. So you express this as a scalar multiplication of this vector. So you multiply the scalars U1 with alpha 1, U2 with alpha 2, U3 with alpha 3. Get the values U1 of alpha 1, alpha 2, and alpha 3. Then likewise, you will do the same for this part here. You need to show that V, which is that, is a linear combination of this, this, and that. So it means you seek for alpha 1, alpha 2, and alpha 3, such that alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3 is equal to V, is equal to V. So place that alpha 1, what is U1? 1, 2, 3. What is U2? Is 2, 3, 7. What is U3? Is 3, 5, and 6. Then what is V? Is the 3, 7, and negative 4. So you need to express this as a combination of this. So this is what you do. So get 3 equations, solve them, get the values of alpha 1, alpha 2, and alpha 3. So if the values for alpha 1, alpha 2, and alpha 3 exist, then it means V can be written as a linear combination of the vectors U1, U2, and U3. And from there, you will be done. So that is how we do these numbers here. So make sure you try out this, get the values of alpha 1, alpha 2, and alpha 3, then write V, substitute them back here, and that will imply that V can be written as a linear combination of U1, U2, and U3, and that will be all. So basically, that is all about our today's discussion. So we have discussed about linear combination, about linearly independent and dependent vectors, and we also defined what linearly independent vectors and dependent vectors are, and we also defined what a vector space is. We looked at different examples of vector spaces. So that's all for today. We shall look at the next question that is about the revision for linear algebra. Make sure you subscribe, like, and share this video to your friends such that everyone is able to benefit from this given session. We meet in our next session.